How's it going, everyone? Sorry for the delay in getting this up. I know it was supposed to go up yesterday, and in that time that I had reserved, I started to think about how we'd actually lay the course out. So I've taught this in 8 weeks before last summer. As you all know, I didn't know that I would be teaching this for sure until Monday, and I really wanted to kind of rethink how we could modify the course and make it better from those 8 weeks. I was playing with assignments and playing with content that I wanted to modify, and it made me realize that I probably do need to do an introductory lecture. So this lecture will have 3 modules. The first, I'll tell you a little bit about me. I realize that I know many of you already, so this won't be, I modified it a little bit. I added an additional slide to talk about that question that I asked you at the end of the initial discussion board assignment this week. Then we'll have 2 additional modules talking about the course structure and what you need to do to get started. And then we'll do the Introduction to Computing for Engineers lecture actually on Friday, and I'll kind of foreshadow why that's important and why you don't want this class to just look like a programming class or whatever that means. And we'll get into all that detail in a little bit, but let's use this module to focus on a little bit of my background. So I know that most of you know, but I'm not from San Antonio originally. I was born in a suburb of Cleveland, Ohio, about 45 minutes west. It is known as Lorain, Ohio. Then if you throw that into to Google, you would see that it is known for manufacturing, particularly automotive and coal. So my dad, he worked for Ford in assembly on the Econoline assembly line, and they used to make the later version of the Thunderbird. For those of you that are familiar with Ford cars, both of my grandparents worked in automotive. My grandpa on my mom's side for Ford and my grandpa on my dad's side for GM, and they both came before that. They moved up from kind of the Appalachia regions of different parts of Kentucky working in coal mining. So I originally attended school in Lorain, but when I grew up, I moved to a rural high school, and there wasn't really much exposure to engineering. I always make the joke that when I was at my graduation party and I told someone that I wanted to be an electrical engineer, which I didn't really want to be, my guidance counselor just said, hey, you can make good money and not get laid off, and you're good at math. And I said, oh, that sounds good. They joked that I could come back and wire their house. And I just kind of said, oh, that sounds great. I'll see you in 4 years. And the reason I bring that up is not to be like, oh, poor me, but rather to say if anything I do impresses you at all throughout the course, and you think that wants to be a pathway that you want to take, wherever you're at or wherever you came from, it doesn't matter. You can go wherever you want in this world. I think I've gotten to work on some really, really cool projects, work with some really, really smart people, and that all started from nothing. So wherever you're at, wherever you want to be, you can go. In terms of my early career, I went to Wright State University, which I'm sure no one has heard of. Sometimes this kind of time of year in the spring, if they happen to win the Horizon League, they'll be in the NCAA tournament, and people will be like, oh, yeah, I know that school. But by and large, people have never heard of it. I went to it because it was the school that I got the best scholarship at, and that's all that mattered to me at the time was money. So you might look at the word Wright State and see that it kind of sounds like the Wright brothers or Wright-Patterson Air Force Base, and that is where it's at. It's in Dayton, Ohio. And again, I was very financially focused because didn't come from a lot of money. So I cared about graduating as soon as I can. So I graduated in 3 years with my undergrad, didn't really worry about doing an internship. And I kind of rushed and I got to the end. And fortunately, I had a very good GPA. So I was able to get a job right out of school. And that was at Air Force Research Lab, working in the Sensors Directorate. And you might be aware that Air Force Research Lab also has a presence here in San Antonio, but the headquarters is in Dayton, Ohio. And I worked in the Sensors Directorate, basically on making antennas that were small and wideband, meaning that they can send and receive information over a broad range of frequencies, so they can support high data rates. In addition, if they're being used for imaging or radar type applications, they have the capacity to have very high resolution, target resolution capacities. Generally speaking, the issue is from a physical point of view, when you want them to have high bandwidth, that typically, it's not an antenna class, so we won't go into the detail, but it's hard to make antennas that have those properties that are small and are planar. And I was working on drone systems at the time, which is why I was interested in those antennas. I worked there for 3 years. I hired in when I finished my undergrad. I was going to grad school simultaneously. I got to the end of the degree and I went to my boss and I said, I'd like a little bit of a raise. I'm making a bachelor's degree salary right now. And he was like, totally cool. But here in the government, we'll have to taper you up and it'll take about 10 years. So I decided to transition into a civilian, a contractor role rather. I was a civilian. at Wright-Patterson as well, actually supporting the Navy through a contractor known as Technology Service Corporation in Bloomington, Indiana is where I live, but the naval operations were actually in southern Indiana and Crane. And I know everyone in Texas is like Indiana's a long way away, but you probably know it's not near an ocean, so it seems like a weird place for a naval base, and it was. We worked a lot on the Aegis radar system and SPS-48E antenna, and those aircraft carriers would come into port, and they would be disassembled, the antennas, and they would be shipped on rail to Indiana, where all of the kind of refabrication and testing would be done. And I worked a lot on the design, kind of more legacy maintenance of those systems. So where did I actually use programming? I joke with people. Sometimes people will watch me code and they'll be like, hey, you're a very, very good coder. And really, I feel like, and I'm sure I haven't done this, but I've tried every day for the last 19 years now to at least code for 45 minutes to an hour a day. So what I actually mean when you talk about coding as an engineer, I work a lot with computer scientists. My main research colleague right now is a computer science professor. We work on applications in cognitive inspired reinforcement learning for CPS, cyber physical systems. If you don't know what that means, it's totally okay. But the point that I'm telling you is I've never actually, I don't have a CS degree, but I did do a computer science minor when I was an undergrad, but I think I'm a very, very good coder. So how did I pick it all up? And what kind of different jobs do actual engineers do in programming? I know that everyone thinks when you think about, hey, I'm going to learn to code, not as much anymore, but when I used to teach coding classes like 5-10 years ago, people would be like, hey, when am I going to build that app? When am I going to build an app for my iPhone or my my Android phone? And when you think about application development, that's what comes to mind when people think about learning how to program. But what do engineers do with actually programming, or what even is it? And we're going to have a total lecture on this, so I don't want to go into a lot of detail. But really, when you talk about programming, you're talking about automating the capacity of a computer to do tasks. And what does a computer do? Well, a computer does computing, which fundamentally is just a fancy way to say that it's capable of doing computation or math. So even all of the kind of applications that we use that we don't think about as math under the hood, whether it's streaming video on a computer or whether it's doing word processing or PowerPoint files, whatever it may be, fundamentally, those all are related to the capacity of the computer to do mathematics. So really, I think engineers spend a lot more of the time in terms of automating that computation, doing a bunch of tasks that are related to data. So one of the things we do is just really automating any kind of data workflow. So you might have a physical test instrument, whether you're going to be an electrical engineer or a mechanical engineer, and it's continuously capturing data. Who's going to kind of automatically get that data off? Most of the times they have a graphical user interface. You could take screenshots. You could write numbers down. That's not feasible for large-scale deployment. So what type of individual is responsible for automating the process of taking data that's being captured on an instrument and actually getting it into a file that can be used later, either locally or somewhere on the cloud? That's an engineering type programming application. You want to do it in an automated fashion. Another thing that's really cool about engineering is you have the capability to maybe do it to a dedicated instrument like an oscilloscope or a multimeter. You have the capability to build your own instrument using some type of embedded computing platform, something as simple as an Arduino or something as complicated as one of, if any of you had the chance to attend any of the NVIDIA GTC sessions, those development platforms that they talked about for computer vision, something like a Jetson or an Orion or something like that. So that's really the differentiation between an engineer and a computer scientist with respect to data importing. Both engineers and computer scientists are expected to be very good with kind of manipulating data that's already in binary in a file on a computer. But if you need someone to actually work and interface with hardware, because of the additional understanding that engineers have of how things work, that's kind of a job that's typically more thought of as an engineering programming application. In addition, one of the things you're going to do the most is data cleaning, right? And data reformatting and so on. This idea of pipelining means you have data in one form and you want to get it to another form, another actual structure, another data type, another application. You always want to do that if you can in an automated fashion. It's just not going to be feasible to manually do those manipulations each time. What do I mean by that? Well, say you had a table of data in an Excel file, and based upon the matter that you captured it, there were a bunch of meaningless numbers. Oftentimes, physical instrumentation will enter NaN, not a number, when a data capture actually can't be measured. Could you just manually go through that entire table and delete those particular entries? Yeah, you could, but that's not going to be a scalable fashion. So the process of actually cleaning that in an automated fashion through programming is one of the key responsibilities of engineers. Ultimately, when you have that data taken in, you've cleaned it, you pipelined it, you have it to the point where you want to use it. What are you going to use it for? Are you going to build some sort of artificial intelligence model that recognizes patterns in that data and makes predictions or infers about new situations? That's going to be something that you do in a programmatic fashion as well. That kind of works a little bit different in the sense that the underlying computation in mathematics that's required to do that has already been captured and coded up in a library by someone. So the question is, how do you actually manipulate or utilize those libraries, or more generally, application programming interfaces in order to achieve that function? It could be that you need to do some type of hypothesis or statistical testing. You have a set of data, you have a belief of how that data was generated. What is the probability that it actually happened? Kind of automating those statistical routines is something that would be an engineering programming task as well. So what are some examples of this? Well, I mentioned when I used to work at AFRL and Crane, I did a lot of antenna designs, particularly computational electromagnetics, which is where you basically put a 3D model of an antenna with the specifications of its material constitutive properties into a software that breaks it up into little pieces and chunks, which is called finite element analysis, and actually predicts what its radiation pattern would look like. So a lot of the antennas that we made, like they were as simple as being I don't want to go into a lot of details here, but just a straight metallic line with little stubs off the end. And the stubs were arranged at a periodic fashion in space. So the length of the stub could vary, or the width of the stub could vary, or the period could vary. And we had some idea based upon basic physics of how changing those parameters would influence how the antenna behaved. But, and I had a software that if I gave it a model, it had the capability to determine that for me. But do I want to manually change that model, change a parameter of the particular antenna every time and they rerun the simulation? That sounds like something that you would want to do in an automated fashion. So that is an example where I used engineering programming in order to allow me to step through the entire space of possible design parameters and capture the resulting performance data and kind of understand general trends in what was going on from a physical perspective. In addition, these antennas were ultimately built and tested inside an anechoic chamber using a very expensive piece of equipment called a vector network analyzer. We were just interested in seeing the data that came out of that VNA. So the process of automating the data acquisition workflow from the hardware to the actual computer that everyone was working on, or to some type of centralized file system where everyone could gain access to it, that was an automated or programming thing. In addition, oftentimes management wants to look at the results of your data, and they don't want to dig into all of the kind of command line or coding level details. So you might have to build an application that's got a drop-down menu and got a GUI to let them see, hey, what happens if I change this parameter from X to Y? This is what changes in the radiation pattern. So building visualizations and what-if analysis in the form of applications that aren't really intended to be used by a mass variety of people, not necessarily a TikTok or an Instagram, but an application that's dedicated to your program manager in order to be able to see your data and do what-if analysis in a quick fashion. When I worked at Wind Supply, which I'll talk about here in a minute, I also have a business background. I did a lot of application development to aid individuals in making capital budgeting decisions. So we had a very large internal software development group, probably about 10 million annually in salaries. But oftentimes we would need new software capability and someone had already made it. So we would have to make a decision of, do we actually go and buy this software, or do we task our individuals that we already have on payroll to code it up for us? And there's trade-offs for both of those, as you might imagine. And the management folks have already studied this problem in a lot of details. And there's underlying mathematical formulas that help you in making this decision. So really just coming up with a tool, developing an application that the end user could take and enter the relevant parameters, how much they would pay for the software and estimates, how long it would take and so on, and coming up with this literally just had a red, green, or yellow light on the end. And really then when they would get the yellow light, or really any of the lights, they would come and talk to me anyways. So I'm not sure it was the most effective tool in the world. In addition, the company was in the process from exploring transitions from being privately held to an initial public offering, and they have all their actual real financial data generated by financial accounting and coming up with projections of what the future cash flows would look like and models to transition those future earnings to the actual equity value of the company. And again, that's a lot of math, a lot of detail, using a lot of really dirty and tons of data. But the end people that want to see this, the people that own the company in the private, in their hands in the private ownership. All they want to know is how much they're going to get on the return on their equity. So coming up with a tool where they can do what if analysis, change some individual parameters, and see a number, they like that tool a lot, as you can imagine. When I was, and I'll get to it in a minute, when I decided that I wanted to go back and be a physician, and I was working, ended up not going to medical school, but doing some additional graduate training in the artificial intelligence and pervasive healthcare space, I used to build a lot of applications on embedded hardware, which is just a fancy way to say cheap computers that don't look like laptops or desktops, in order to do different types of sensing applications. Oftentimes that was on the Arduino programming microcontroller. Sometimes it was on some sort of phone or so on. But as we'll see when we get into the engineering computing module, even though those don't look like computers as we would traditionally call them, they do satisfy what is known as the Turing test in order to be Turing complete and programmable. So they are computers. They meet those 3 von Neumann architecture criteria, and we will define that in a minute. And then most recently, when I moved to Texas, before I went back to teaching and kind of administration and higher ed full time, I did a lot of AI model development for eye tracking data that was integrated into head mounted devices like augmented reality and virtual reality platforms. And that required just really end-to-end programming, data coming out of hardware, actually grabbing from that hardware, bringing it into a computing environment, cleaning, manipulating its format, actually training AI models, doing prediction, and reporting that information via visualization out to management. So that's just an idea. If you're like, when I'm like, hey, what are you going to be doing with programming? Well, it really depends on what kind of engineer you're going to be. But by and large, what you probably will be doing is some sort of automation of the computation associated with data workflows. So I transitioned to higher ed. I've done it twice. In the 2009 period, after I had worked in antenna design and did graduate school originally, I decided to teach full time from 2009 to 2011. I was in my hometown of Cleveland, Ohio, teaching largely individuals that were interested in kind of being able to repair, diagnose, and upskill and coach individuals about medical diagnostic equipment for the Cleveland Clinic. We did have a transfer program similar to what we have here as well, but it was more workforce oriented in terms of the number of courses I taught. At that time, I kind of developed an interest in medicine and applications of how we could become more efficient at delivering medicine in a better fashion than we do now. And that was around the time of the Affordable Care Act as well, some of you might remember. So decided to go back to medical school, and I've ended up kind of taking a position where part-time I was finishing my MBA. And the only reason I did that was if I took that job and I taught, and that's how I kind of earned my check. And I taught in a manner that I got a free MBA. But I also, at the same time, was taking my med school prereqs. And I took the MCAT, did all that work to get into medical school, and then decided I would be too old by the time I finished up. But rather than just kind of abandon the idea of the medical training, the way I was going to pay for med school was doing another graduate degree in electrical engineering at the same time. So I decided just to focus on that opportunity to work more in engineering and do additional training in artificial intelligence, particularly when people ask what kind of research I do. I say I work in sensor analytics with a focus on ubiquitous healthcare applications. What that really is a fancy way to say is looking at some problem in healthcare that could benefit from automated decision making, or which is of course implemented through artificial intelligence, asking myself what kind of data would be necessary in order to build those AI models, and actually building the hardware in order to capture the data, building the AI models, and taking it from an end-to-end fashion. So really, to me, that's one of the nice things about being an electrical or computer engineer versus a computer scientist is you can do those sorts of things. You don't just have to say, well, I would need this kind of data. Well, that kind of data doesn't exist. Oh, well, too bad. I guess I'll work on a new problem. You can actually be someone that actually goes out and builds a system to get the data as well. So that kind of led to a focus on embedded eye tracking. The eye is the window to the brain, of course. So that's why I'm most interested in those types of signals now. So I transitioned to Texas, working on a couple funded projects for Meta and Google in the area of eye tracking for mixed reality applications. The Meta project was Project Aria, and Google was all about a project to integrate non-video based eye tracking into the platform that they were working on for augmented reality at the time. Basically, the key for that is most eye tracking now works by taking a video of your eye. So there's a limited frame rate at which you can do that. It's very computationally expensive, and you actually don't need the majority of the pixel information in that video that you capture. So what if you could do a non-video based approach that would be allow you to do it with less power consumption and allow you to grab a higher sampling rate of data. So after I did that for about a year, I decided to kind of transition into administration. I was the associate director of the Matrix AI Consortium at UTSA. And while I was doing that, I was teaching part-time in electrical and computer engineering as well. And after I transitioned to Stack, I stayed active in the UTSA ECE department. I still teach over there and also advise undergraduate and graduate students in their research. And I do remain active in research. Here are just a couple of publications. I need to update these. They're a little bit dated now. But particularly, when you're at SAC and we don't really have a strong research presence, you rely heavily on collaborations with external individuals. So work a lot with Texas State University, as I mentioned earlier, the computer science department, UTSA ECE, and then my old friends at Michigan State University still. So in addition, if any of you are really interested in learning programming or whatever you're doing in engineering, if your goal is to eventually transition into a startup or a new venture formation, I do have a couple graduate degrees in business, an MBA with more of a finance, valuation, and project management focus, along with a master's in management science that's really focused on quality, statistical process control, Six Sigma type stuff. So if you're interested in that, feel free to reach out. And if you have an idea and you want to build the tech to start a company and you're invested in how to do it, I am very interested in that as well and can help you find resources within the local community that can make that happen for you. So we will resume the next lecture and we'll talk a little bit about the learning objectives for the course along with the schedule of when we will actually hit those.